Folks, in this pre-work, we're going to look at a variety of Laplace transformations that will combine together to be able to answer some more interesting initial value problems. And a number of these transformations have to do with shifting Laplace transforms around in various ways. And this might be a little bit difficult to keep track of, but I'll do my best to sort of sort it out for you as we work through it. The first thing I want to say is that if we multiply a function by e to the at, that's going to delay f of s by a units. What do I mean by that? I mean that if we were to take the Laplace transform of e to the at f of t, that this is going to be the Laplace transform of capital of f of s minus a. And so if the Laplace transform of f of t is capital F of s, in fact, let's write that, where the Laplace transform of f of t is capital F of s, then the fact that we multiplied the function by e to the at simply took the graph, the function f of s, and shifted it a units to the right. And that's why I want you to think about it as delaying the function by a units. So let's go ahead and prove that. Suppose f of t is piecewise continuous and of exponential order. Why do I have to say all of that? That just assumes that the Laplace transform of f of t exists. Then if we go to compute this, we get the Laplace transform of e to the at f of t would be the Laplace transform, which would be by definition the integral from 0 to infinity of e to the at f of t times e to the minus st dt. So this was our function, and the Laplace transform says to do this integral with that modifier multiplied to it. And so if we clean this up, this becomes the integral from 0 to infinity of just f of t, and if I combine those exponential terms, I can rewrite that as e to the negative parentheses s minus a t. And double check that arithmetic, but yes, we've got a minus s and a plus a there being multiplied by t dt. But this is simply the original Laplace transform, except I've got an s minus a where I normally have an s, and so that would just be capital F of s minus a. So there we've shown that if we take a function, especially if we already know the Laplace transform of that function, and we multiply that by e to the at, it'll just be that function's Laplace transform, but shifted to the right, a units. Let's put that into practice. So in this problem here, we'd like to compute the Laplace transform of e to the at cosine bt. So the Laplace transform of e to the at cosine bt, well, we know that the Laplace transform of the cosine of bt is simply s over s squared plus b squared. And so in this case, this Laplace transform would be the Laplace transform of the cosine of bt, but we need to shift it a units to the right. So I'm going to take this transformation that I already know, and everywhere I see an s, I'm going to replace it with s minus a. So this is going to give me s minus a all divided by s minus a quantity squared plus b squared. And so this is a Laplace transform that I've actually had you use a few times, but now we've finally proved it. So let's go ahead and try another one. Let's do the Laplace transform of e to the 5t sine 2t plus e to the minus 2t t to the fourth. And so I know the Laplace transform of the sine of 2t. So that would just be 2 over, and normally I'd write an s here, but I'll put space squared plus 4, where that's b squared. But because, so that if I had an s here, this would be the Laplace transform of the sine of 2t. But because I'm multiplying my known Laplace transform function by e to the 5t, I'm going to take that known Laplace transform and shift it to the right 5 units. So this gives me s minus 5 sitting in there. Likewise, I know that the Laplace transform of t to the fourth should be 4 factorial all over, and then normally it is s to the, in this case, 4 plus 1. So normally it'd be s to the 5th. But because I'm taking the function t to the 4th, whose Laplace transform I know, and I'm multiplying it by e to the at, I'm going to take the transform of that function and shift it to the right a units. Careful here, in this case, since a is negative, that would be s plus 2 inside of that. Let's clean that up just slightly. So this gives us 2 over s minus 5 quantity squared plus 4 plus, and then 4 factorial is 24. So we get 24 over s plus 2 to the 5th. So taking, using 2 and 3 here as examples, I'd like you to try to compute the Laplace transform of this function here. Give it a shot. Folks, if after you've reviewed 2 and 3, comparing it to this theorem that we've given, if you still can't compute number 4, please come by and see me as we run up towards the end of the semester. It's really important that you get your questions answered as soon as possible. That's all I've got in this video, and I'll see you in the next one.